Welcome to another podcast. In this episode, we're going to be taking a look at an application of Taylor series and Maclaurin series to calculating limits. So if you remember limits as a topic from Calculus 1, there are just some really difficult limits that involved L'Hopital's rule, and sometimes you had to do L'Hopital's rule repeatedly in order to figure out what the limit was, and it wasn't always the easiest thing. It turns out that series can help make that process a lot easier because you can be dealing with polynomials for certain functions rather than things like cosine, sine, exponentials, things we know the Maclaurin series of. And so I wanted to take a look at this example with you. We're going to start off by just simply evaluating the limit as it is and show that it is indeterminate. So if I try to plug in this case, x equal to 0, then if I make x 0, I get 0 plus 2 minus 2 over 0. Which that ends up being 0 over 0. So this is indeterminate of type 0 over 0. So L'Hopital's rule would apply. And, if you tried to do L'Hopital's rule here, this would be the limit as x goes to 0. If you take the derivative of the top, you would get 2x. The derivative of cosine is minus sine, so this would be minus 2 sine x. Over 3, so this would be 12x cubed at that point. Notice that if you were to evaluate this at x equal to 0 again, you would get 0 on the top, and you would get 0 on the bottom, so you'd have to do L'Hopital's again, so on and so forth. In fact, for this problem, you would have to do L'Hopital's 4 times. So 4 times you'd have to repeat the application of L'Hopital's rule before you would actually get something to come out of this limit. So instead, I want to use series to my benefit here. And the way that I'm going to do this, so we're not going to do it this way. Instead, the way that I'm going to do this is by thinking of the following. I'm going to let the limit as x goes to 0 of, and I'm going to replace this cosine with the power series form. Now, I'm not going to put the sum in here. Instead, I'm going to put the series in its written out term by term form. So we know that cosine looks like this. So it's x to the 4th over 4 factorial, which is 24, minus x to the 6th over 6 factorial, which is 720, and so on. So minus 2, so that is the numerator. And then for the denominator, we have just 12x cubed. And so, 3x to the 4th. So we have just 3x to the 4th here in the denominator. Now, I'm not ready to apply the limit as x goes to 0 yet. What I'd like for you to see is if we make the calculations here and look at the terms that are involved. One of the things that you immediately see is this 2. The first term here is 2, and then this is a negative 2. So those will cancel. And then you've got x squared minus the x squared, that's the first term here. So you can see how that numerator is going to simplify down somewhat. And in fact, the first term of the numerator would be x squared minus x squared over 2. You would have that piece, but then you've got the 2 here. So you get x squared minus x squared at that point. So those would be gone as well. So this would cancel with this. And so the very first term that you would see would just be the x to the 4th over, remember the 2 here, so it'd be 2 over 24, x to the 4th over 12. And then the next term would be minus x to the 6th over 2 divided by 720 would be 360, plus, and you would just have that infinite series remaining. All of the other terms went away. And then in the denominator, you have this 3x to the 4th. And so one more step here, if I was to simplify that once again, then if you look, x to the fourth divided by 3x to the fourth, and you've got the 12 in there, that's the same thing as 1/36. So if I take this term and divide it by 3x to the fourth, I get 1/36. The next term, I get minus x to the sixth divided by x to the fourth gives you an x squared, and then you get 360 times 3, which is 1080. Plus the next term would be an x to the eighth, which would leave an x to the fourth and change, but the point is all of these terms involve higher powers of x. And if you take the limit as x goes to 0, which we're supposed to do, then this goes to 0, and so do all of those other terms. The only term which survives is the first term here that doesn't have a power of x, and that turns out to be the answer. So the limit, and you can verify this, do L'Hopital's rule another couple of times, you can verify that the limit of this series is 1/36. Or excuse me, the limit of this expression using series is 1/36. And so this is a common application of Taylor series, of these Maclaurin series that we've been working with, in that you can substitute them for functions involved in other processes and look at seeing if it simplifies the problem. In the case of the limit here, it does. So this is just one of the many applications that we're going to get out of this unit. All right, thank you for watching.